Let's get rolling, Calcsters. I didn't have anything funny to say. I learned a bunch of new Gen Z words this morning, but all I remember is 41, and I don't like it. I don't know. They're doing that. 6, 7, 41. I don't know. I don't get it. All right. So, here we go. Gosh, good audience today. Love it. Okay, we're going to sneak in a couple theorems real quick. Now, remember that when we're dealing with theorems, theorems are mathematical ideas that something really important has had to happen to them to become a theorem. It goes from a conjecture to a theorem once we do something. You prove it. Okay, here's good news or bad news. Proof. Love or hate? Okay, well, I guess this is bad news then. We do not do proof in here. Okay, proving calculus is its own field of mathematics. It's called analysis. When we get a little bit more experience with calc stuff, I'll show you my old analysis, one of my old analysis textbooks, and you'll tell it's calculus, but it's much more involved. So, starting today, we are still in 1.3. We're going to finish it and have some time for homework, and let me just see what we have to hit. Don't have notes, that's all right. So looking at this, we're going to get some theorems that we work out with, or that we get. So theorem, and I use THM, theorems with continuity. Now, for these, we will get more and more theorems later. Typically, they present us as shortcuts or something that we'll use when we're doing bigger parts of calculus. These don't have numbers, so we're just going to list a couple of them and see if we can make sense of what it actually means. So first and foremost, if I give you a polynomial function, and can somebody tell me what a polynomial function is? I know that there's many nomials just based off the name. What is a polynomial? Okay. I think you guys will be able to spot it. Like, you'll remember once we do it. In red, I'm going to write the general definition for a polynomial. It's ugly, but they're not all ugly. A polynomial function will have the form f of x. Then we have some leading coefficient, a sub n. And then we just have x to the power of n. Plus some different, possibly, coefficient, a sub n minus 1 times x to the power of, any guesses? N minus 1. This keeps going depending on how big n is, right? Eventually, we'll get down to plus a sub 1, eventually, x to the 1, plus possibly some constant that we call a naught. N-A-U-G-H-T, not N-O-T. A sub 0 is a naught. Okay, do you all remember seeing this last year? It looks really ugly, right? Can you give me, just speaking, I don't want to write them all, can you give me some examples of polynomial functions? Rafa, give me one that fits this. You don't have to go all the way through.
Like x squared plus 2x.
X squared plus 2x, does that follow this pattern? What's a sub 1, or a sub 2, I guess in this case? What's the term, the coefficient of the x squared? 1. And a sub 1, 2, and a sub 0, the constant that I added on the end? 0. It just didn't exist. Anytime that you write it without dividing by x, taking square roots, you're using nice integer powers, and you can write it like this. I don't care if it starts at 5x to the 50th and counts down or skips some, doesn't matter. Those are all polynomials. They all produce nice, smooth, continuous curves. Okay, that is what our theorem is going to tell us. A polynomial function, if you want to write the general form, here it is continuous, and I'll actually write the word here, but you guys can use this shorthand. That's not right. Continuous. Okay, hook it up. What is this? For all, and what is this? Okay, this says a polynomial function is continuous for all real numbers. Again, I'll do this for the first few days. For all real numbers. Okay, boom, easy. Okay, beyond this, another little theorem. And we'll get names for big important ones, just so you guys know. But as we're looking, we also know that a rational function, which when you see rational, what is a rational function going to be? A fraction. Not the word that I was expecting based on what I did, but I love it. Fraction. Give me another word for fraction. A ratio. Okay. A rational function is continuous on its domain. We can beat that. All right. I'll go and kick the door closed. Give me an example of a rational function. Too many answers. Just one person. Who haven't I called on? Anybody remember writing n of x over d of x last year? For a numerator, it's a function, and denominator is its own function. If you write something that has x up top, maybe x up top, or x down below, or a combination, like 1 over x, that's a really simple one. 1 is a polynomial, it's a polynomial, but it's nice and smooth. X is nice and smooth. With a rational function, it has a hole when x is 0. Can't divide by 0. So that thing's domain is all numbers except 0. It's continuous everywhere except 0. But it's not in its domain, so we say it's continuous on its domain. There was a lot of talking there. We'll see it. Don't stress. Okay, rational functions are continuous on their domains. Cool. Let's see if we can get another one. Ooh, here we go. I'm not going to write this. If f and g, so we get like 4 theorems today, just so you know, 5. If f and g are continuous, are functions, and we can say continuous functions at x equals, I don't know, c, and I'm going to ask you guys to read this. I'm going to write it. K epsilon blackboard R. F and G are continuous functions, and they're continuous at some number, x equals c. What does this next part say? And what? K is in the set of real numbers. So we have another number k that's real. Well, then we get all of the following, and I'm trying to see why I included k. Weird. We'll deal with that. Okay, then we get 3 consequences, and I'm going to list them all with bullet points so it doesn't look like negative. If f is continuous and g is continuous, what do you think we can conclude about f plus g? And I'll say of x, just so it looks a little nicer. If f is continuous and g is continuous, what do you think is going to be true about f plus g? It's continuous. Can I, instead of writing another line, I'm just going to change one thing. If f plus g is continuous, what do you think about f minus g? It's also continuous. And check it out. We're just going to use plus or minus here. All right. How about this one? What if instead of f plus or minus g being continuous, we did f times g? Notice I'm not using the dot for a very specific reason. What do you think we're going to conclude about the product of these two functions? It's continuous. Huge stretch there. Two more rather. What if I take this number k and I multiply it by f? So it's just some constant multiple out in front. If f was continuous, is 2f continuous, do you think? Like, check it out, and I can see that there's not really a whole lot of confidence in this. X squared is a continuous function, right? Is 2x squared? Yeah, okay, I'm cool with that. Kf of x is also continuous. There's one more that I'm leaving out. Division. If f and g are both continuous, then f over g is also continuous. Is continuous. Are there any little caveats that maybe we need to pay attention to or be mindful of? G can't be equal to 0, right? So as long as that doesn't happen, we're okay. Yeah, we get 4 basic functions here. Next one. This one is the hardest continuity and limit property. And they're all, like, I know we haven't used limits today at least. They're all linked together. Limits and continuity go hand in hand because we need the limit to exist to be continuous. So we're talking about the same idea, just from a slightly different point of view. Okay, one more. If Before we commit, let's see if I can just use the same one. Yep, I'm good with this. This one will have two parts to it. What is this symbol? So this is f of g of x, but we don't say of as the operation. What am I doing with these functions? Composing. Okay, if f and g are both continuous at the same c value, then f of g of x, then f of, what am I doing? What should I write here? Why am I getting weird? Is what? F of, notice the pattern. Can we just say it's continuous? Okay, yeah, sorry about that. I was trying to rewrite the whole theorem. Didn't need to. Now, here's the big takeaway. These are all theorems. They're standalone theorems in your textbook. Oftentimes when we use theorems, we have one big idea, and here it is, and then we get a bunch of more things that come out of it, but they're not really their standalone ideas. They're just immediate results. They're called corollaries in math. So theorem and results from that is called a corollary. We get a corollary, or something that we at least want to pay attention to, and we're just going to get a limit property sneaking in here. If I try to take the limit as x approaches c of a composition, f, do you want me to write composed with or f of g? Okay, and then I should check, Leanne and Aisha, have you guys seen this notation? Like, this is familiar? Okay. Aisha? Okay, you should come in at lunch and I'll get you caught up. Okay. How about, before I say that, how about this last notation, f of g of x? Okay, same symbol. Same thing, they're just written differently. Okay, if you were to take the limit of this, gut feelings? Don't care if you're wrong. What's your intuition say? Like, we've seen the limit stuff moves in other situations, right? Where could it move? And I'm just looking, I'll write them up here, we're going to write them on the board. What are some possibilities? Good ideas are, yeah, just shout them out. Inside, what moves inside? I like it. I don't know where my eraser is, so we're just going to, so what, how would you want me to write it? Sorry. So, like, just move this, like move this bracket? You could do that. The other things that I'm thinking, and let me know if this came to anybody's mind. Anybody think it might become something like the limit, and this is what Riley said, so I'll just write this one, x approaches c of f of g of x. It could just do that, right? Certainly possible. Another situation, it could be f of the limit as x approaches c of g of x. Is there another combination of these that we could do? I mean, it could switch to g of the limit, but that'd be weird that it would switch directions. One of these, they're both correct, honestly. This one is just what we wrote. I just didn't put the brackets around it. This is our property. Anybody have that gut feeling that it goes inside somehow? Like, I think you did, based on that. I don't know that that is exactly what you meant. I'm not sure. Maybe. Can't tell. Cool. Here we go. Turns out it is exactly the second one. We just take f of the limit of g. And then check this out. I want to notice something. G was a continuous function, and it worked nicely, which means I can just use direct sub, because it was continuous, nice polynomial type function. This would just equate eventually, on our next step, to be f of g of c, if we're looking at continuity at a value. The limit goes into the inner function. Okay, language-wise, we're going to clean this up. You can write this or commit it to memory, because we will be talking about compositions. If I have f of g of x, what's the outer function? What do you think I'm referring to as the outer function? Has that thing been turning on all year? It feels loud today compared. Okay. Okay, outer part can be hard to answer. What's the inner function? Okay, with confidence, that one came out. This is the inner function, which means, what's the outer function? F is my outer function. Okay, we are going to see this showing up over and over and over. We'll do a few limits with it. That's fine and dandy. Cool. Gosh, we have so many theorems, more than I thought. I'm sorry. I'm not going to write this one. We're just going to say it. If f is continuous and it has an inverse, f inverse, do you think it's continuous? Yes. Yep, absolutely. I'm not even going to write that one down. That one, we'll deal with it when it comes. All right. We get the big theorem now. And sorry, it's kind of boring. Do you want to do a quick brain break? Like this one's kind of bleh, because it's just a bunch of properties and stuff. Okay. The big theorem. So these are all theorems in your book. You'll see them. Sometimes they do prove them. We will do some derivations in here. Very seldomly will we do a proof. Like legitimately 1 or 2 this year, maximum. Okay. But this one is so big that it's going to get its own little tilde. So here we go. The idea today, and this is going to take us about 5 minutes, and then you're going to have time to work on stuff. We get to talk about the first big theorem that we have, and it is known as the intermediate value theorem. The intermediate value theorem. You will never see me write this again. We will work so closely and develop such a good relationship that we develop pet names. What are we going to name our boo here, the intermediate value theorem? Gosh, what a cute name. Cool. The IVT. We have it. Okay. Now, there's a bunch of different ways that we can phrase the intermediate value theorem. I'm going to do it pretty rigorously, but I'm going to open it up to make sure that we all truly understand it. So here we go. On this, if f, and here's our theorem, if f is continuous on the closed interval from a to b, I'm going to say for all x in the closed interval from a to b. And again, I just want to stress, Mickey, I haven't called on you today. What does this say? Gosh, my ears and eyes are so itchy. I'm just trying to maybe give a hint from somebody if you picking up what I'm laying down. What does the A stand for? Did nobody help when I was just distracted? Gosh, again, it's so itchy. What is it? For all x. For all x in, and I'm going to be really wordy. You do not have to write it, but this is helpful. In the, what sort of interval is this? Closed interval. And can I stop writing, or do you want me to write from x equals a to x equals b? I'm not going to. Cool. If f is continuous for all x in this closed interval, and f of a is not equal to f of b, we require that part. Then, we're going to get a new symbol. Okay, I'm going to erase this just so mine looks a little nicer. When I introduce symbols, I am going to propose the following. I'm going to say there exists, and then what I'll try to make the norm, and you guys need to help me remind me, there exists. I'm going to underline this, and then in parentheses we're going to learn the shorthand. Okay, if f of a is not equal to f of b, then there exists, backward capital E. That is the symbol for there exists. There exists at least one number. At least one number. And I'm going to call this number C, and it's going to be in the open interval from A to B, for which, and I'm going to let you guys catch up, sorry. So we have a continuous function that goes from A to B, and they're not equal at the function. Then there must be one C in between those endpoints, for which f of C, I don't know why that came out as a capital C, f of C is equal to n with f, and I'm trying to think of how I want to word this. With n between, f of A and f of B. All right. This is kind of formal mathematics. And by kind of, I mean this is very much formal mathematics. This is how the theorem, I've changed a few of the words, but this is how the theorem is presented in your text, in any text you encounter. F is continuous on a closed interval, and the endpoints are not the same. Then there's at least one number C in that interval where I get a value between them. You guys have actually used the intermediate value theorem today. When? Oh my bell ringer. Hold on, let's just look. Is F continuous on the closed interval? It is. That's A to B, right? And I told you what f of A was and what f of B was, and you decided that there's a number n, happened to be 0 this time, between them. This is the IVT. This is the intermediate value theorem. Should we take this and get a nice little picture? Okay, check it out. I'm going to work in quadrant 1 purely because it's nice. Here's my closed interval from A to B, and I'm going to put some points. Do you want my function to be increasing or decreasing? Increasing. Okay, so I'll put A, this point, don't even mark it. And could it be both? Like, could it do something? It could just do this. That's a boring function. But could it do like something completely wonky and still be okay? Could it do this? Do I still follow the same rules? Is my function continuous from A to B? And defined at A and B? Yeah, we hit all these rules, right? Okay, so quick check. I'm going to name this function f. And I want you guys to help me determine these y values that I just placed. This is what? F of A. What about this one? F of B. Now, I'm going to pick completely at random. It's not really random, right? Because I don't think I can actually be random. But I'm going to pick any number. You guys just shout where to stop. Okay. Here's n in this context. As long as it's between them, I'm okay with it. Is there a C value down on the x-axis that when I plug it into the function, it spits out this n value? And if I look at it, and I'm just doing it here, to me it looks like on this one it'd be C right here. That point existed. I could do it. We used this earlier to identify a 0, and it doesn't really matter where n goes. I wouldn't put a bunch of them on your page, but could I have chosen to put n right here? Yeah, and at that point, check it out. Here's my C value. Last question, definitely don't write this one. Why can't I choose n? If I keep saying I can put it anywhere I want, why can't I do this IVT if n is here? What do you mean? There's a C value right here that hits it though. That's what I needed to hear. That n value that I chose could exist. Like maybe there's a value here, and there is on this function where this is it, but the theorem says n must be between these. Cool. Seem okay? Where might we ever use the intermediate value theorem? Okay, we're going to check it real quick. One really quick example, and this isn't really truly calculus, but before we move on, questions, any part about this? When we teach this, when I teach this in pre-calc, we use it to find zeros typically. Cool. I'm okay. Here's the deal, because this is not really a calculus problem. I'm just going to demonstrate this. You guys are cool to just listen. You can work along if you want, but I just want to show us that, like, how this works. And we're going to look at a function. I'm going to deal with this function. F of x is x cubed plus x squared minus x minus 2. Couple quick review questions for you. Is that a polynomial? What's its domain? All reals. We had a theorem today that said polynomials have domain of all real numbers. It's a polynomial, its domain is all real numbers, and it's continuous, right? Okay, if I wanted to check a couple values, real quickly, I just need your help. F of 1. 1 plus 1 is 2, minus 2 is 0, minus 1, it's negative 1, right? Okay, F of 2, a little harder. 8 plus 4 is 12, minus 2 is 10, minus 2 is 8. What can I, with confidence, claim there must be between 1 and 2? A 0, right? A root, an x-intercept. The IVT, and all we would say, and this is just highlighting it, by IVT, f has a 0 in, why would I write in? We have a symbol for this. In the interval, what interval do I guarantee the existence of a 0? -1, sorry, not -1, 1 to 2. Why won't I undo? There it is. Somewhere between 1 and 2, I must have crossed the x-axis. And I can see that because I must have been equal to 0. That's our IVT. We used it at the bell ringer, we used it just now. Cool? All right. Continuity, any easier or harder than limits? Does it feel different? Does it just feel like the same stuff? See how it feels. All right. So we're going to see. We'll see how it feels. We have an assignment. Don't remember what it was. Your book always gives really long assignments. We're going to take a little time trip real quick. All right. Here is your assignment. It's not due on the 31st of August in 2021. This is due 9/5. What? Cool. I'll let you guys do it to it.